All right, so in this video, we're going to talk about the polar coordinate system. Before we start that, let's have a real brief discussion and review on the rectangular coordinate system. So in the rectangular coordinate system, generally speaking, we'll have an x-axis and we'll have a y-axis. And if we want to plot a point, let's say 3, 2, then we would count from the origin over 3 units to the right and 2 units up. So there sits our point. And again, counting over and up kind of constructs this rectangle, hence the name rectangular coordinate system. So none of that's new information to you, but we're using it kind of as a foundation to now building into a new coordinate system, which is called the polar coordinate system. Now, the polar coordinate system does not consist of x's and y's. Instead, the polar coordinate system has ordered pairs r and theta, where r is a directed distance and theta is an angular direction. So r is a directed distance, theta is an angular direction. So over here on the side of the screen, I have a polar coordinate grid. Again, it looks very different than the rectangular system grid. It looks like we have a bunch of concentric circles, and that probably wouldn't surprise you any because how often we've talked about the unit circle. But this here in the middle, it's no longer called the origin. For a polar coordinate system, this 0, 0, this is called the pole. And so if you start at the pole, you can see if we count out, we're on the first circle, the second circle, the third circle, the fourth, and the fifth, and we can keep going if we needed to. So this would be where your R values are positive. So when R is 1, R is 2, R is 3, R is 4, etc. When R is negative, we'd have R equals -1, -2, -3, -4. So we'll take a look at the ordered pair 4 pi over 3. So start at the pole, and we'll go ahead and we'll count out 4 circles in the positive direction. 1, 2, 3, 4. Then, since pi over 3 is positive, we're going to go in the counterclockwise direction around to pi over 3. So this is the point 4 comma pi over 3. Right there. Okay, so instead of x's and y's being over and up or over and down, polar coordinates will be out and around. Move out a distance of r and around a distance of theta. If r is positive starting at the pole, you'll move this direction. If r is negative starting at the pole, you'll move this direction. Theta being positive means the same thing it always has, going a counterclockwise direction. Theta being negative means going a clockwise direction. All right, so now we're going to look at how polar coordinates and rectangular coordinates are related. And so we'll draw a picture that I feel like we've drawn a couple thousand times this semester. I'm going to label this the x-axis and the y-axis. And I'm also going to label it 0 and pi over 2. So I've got both the rectangular system and the polar system kind of overlapping each other here. And I'm going to have a point now. This point right here in the rectangular coordinate system would be the point xy. In the polar coordinate system would be r theta. Now, let's think rectangular for a minute, x's and y's. Well, how did we get to that point? We moved over a distance of x and we moved up a distance of y. In the in the polar coordinate system, how did we get there? We started at the pole, we moved out a distance of r and around a distance of theta. So the red will get you there in the rectangular, and the blue will get you there in the polar. Now, again, this triangle is very, very familiar to us. We can see that cosine of theta would be x over r. We can see that sine of theta would be y over r. Now, this means that x equals r cosine theta and y equals r sine theta. So these are helpful in the sense that if you are ever given something in polar coordinates and you want to convert it to rectangular coordinates, you can. If you're given something in polar, you know r and theta. Just plug r and theta in and it'll spit out the x and the y. Now, to go the other direction with this, we'll just make the observation that r equals the square root of x squared plus y squared by the Pythagorean theorem. We can also see that tangent is going to be y over x. So these two now, these allow us to convert from rectangular to polar. Given x and y, we plug them into those formulas and we end up with r's and thetas. So those two formula, or those two boxed in conversions, will allow us to go from polar to rectangular and rectangular to polar depending on the situation. So in the first example, they give us the point 6 negative pi over 4, and they tell us to convert to rectangular. So what that means is we've been given polar coordinates r and theta, and they want us to convert this to x and y. Well, we remember now x equals r cosine theta and y equals r sine theta. So I really just need to plug in the r as 6, the theta as negative pi over 4 for both of these. And then simply evaluate. So this would be 6 times 1 over root 2, and this would be 6 times negative 1 over root 2. And this one is worth cleaning up a little bit. If you rationalize and simplify, you get x to equal 3 root 2 and y to equal negative 3 root 2. Now again, be really clear with your final answer here. They are asking for a point, so let's make sure that we give it in as an ordered pair. So there would be 2 points, this one in rectangular coordinates, this one in polar coordinates. That'll get you to the same place. So in this example now, they're giving us something in rectangular coordinates, x and y, and they want us to convert it to polar, r and theta. So r, we know, is the square root of x squared plus y squared. So when you plug that in, you find out that r equals the square root of 2. And for tangent, we know that's going to be the y over x. So tangent would be equal to negative 1. And this is where you do want to be a little bit careful. We know that there are multiple answers for theta, so we want to make sure we give the correct one. Notice that in the rectangular coordinate system, which is where we started, we're at negative 1, 1. So we're up here in quadrant 2. So that's the angle that we want to make sure that we give here. We want to make sure to give this guy right there. So when you draw your triangle, when you do your labeling, you find out the reference angle would be a pi over 4. If the reference angle is a pi over 4, then this would have to be a 5 pi over 4 for theta. Okay, so do whatever labeling you need to, but theta should be 5 pi over 4, putting us in the correct place. So again, you've got as an ordered pair, root 2 comma 5 pi over 4. All right, so now we're ready to actually convert a rectangular equation to a polar equation, which is not very difficult. As long as you know what x and y are, it's just a matter of substituting it in. So y we know is r sine theta, and x would be r cosine theta. So now, just like for rectangular coordinate systems, we try to solve for y if possible. For polar, we try to solve for r if possible. And to do this, we're just going to have to add 2r cosine theta to the left. We can now factor out an r, and then finally we'll divide off and be left with 5 over sine theta plus 2 cosine theta. And what's most interesting about this problem is that we know this very, very easily is a line. But something like this, which looks nothing like what we're accustomed to seeing, is actually the same as what we started with. It's just now in polar coordinates.